we get our start here in organic chemistry. And some people love this, and some people get very frustrated by organic chemistry. Perhaps the frustrating piece is we've learned a lot of chemistry. Now we almost have to learn a new type of chemistry. Organic chemistry is fairly specific. Again, if we're looking at organic chemistry, just really generally, we're looking at carbon compounds. So it is based on carbon compounds. So that is the unit. That is organic chemistry. Anything with carbon as our base unit is organic chemistry. Now you'll notice in the other chemistry topics we studied, we never had an introduction. So 10.1 in your book, and also called 20.1, is called introduction. And in the standards, it is called introduction. So you know we're in for kind of a big topic if we have an introductory unit to it. So this starts on page 366, and this 10.1, this introduction, is going to be covered in a couple different videos. I'm not going to try to throw all of this at you at once. And again, notice it is 10.1 and 20.1 at the same time. So when we get to that point that that some higher level material comes up, I'll let you know. So that standard level people aren't worrying too much. Okay. So really, what we have to start at is we have to start looking at carbon chains, and we have to start looking at how we draw them and how we name them. That really is our introduction. It's not too bad. It's a nice introduction. So we're going to start our discussion looking at a homologous series. So an homologous series means a series of carbon chains that increase by a CH2 group. Okay, they're successive members of a series. They increase by a CH2 group. So notice just some simple organic compounds to start. We have methane, ethane, propane, and butane. And notice the only difference in each of these is they each have one additional CH2 group. So methane is CH4, and notice up here, C2, one more extra carbon, two extra hydrogens. One extra carbon, two extra hydrogens, and so on. So that is an additional CH2 group. These are all members of an homologous series. Okay, and again, it'll make more sense as we go on. Just know right now it's a homologous series when we add a CH2 group to something. One other thing we might want to notice here that'll help us further on is that these are base names. One carbon, if you ever have one carbon, it is a methyl group. So it starts with that prefix meth. 2 carbons is eth, 3 carbons is prop, and 4 carbons is bute. Now that ending ane is telling us it's an alkane. Okay, that's another important word, and we'll get to it later on. But an alkane are singly bonded carbons. So carbons with only single bonds are alkanes. So it's a methane, meaning it's an alkane. Ethane, meaning 2 carbons that are all singly bonded. Propane, meaning it's 3 carbons that are all singly bonded. And butane, meaning it's 4 carbons that are all singly bonded. Okay. We'll obviously have a lot more of this, but let's go on. Okay, so like it says, these members of this homologous series can be represented by the same general formula, and it gives you a little key here of how to write them. Normally, I don't memorize that equation. I will write out the number of carbon atoms and attach the hydrogen atoms where I need them, because we know each carbon needs 4 bonds, whether they're double bonds or single bonds. So it's pretty easy, I feel like, to write the carbon chain and attach the hydrogens as needed. But again, that equation is there if you want to use it. Now notice we have a new homologous series, but it's still a homologous series. The difference here is now we have an alcohol group. This OH is an alcohol group, so it's an alcohol. And it's still a homologous series because the difference between each of these alcohols is that they have an additional CH2 in them, another carbon and 2 hydrogens. So we have another carbon and 2 hydrogens, and we just happen to have an alcohol in the end. So notice this alcohol group, this is called a functional group, and we have to learn a bunch of functional groups, but it's an OH group, and it's going to be at the end of our formula here, written as OH. And obviously this can still be an homologous group. Notice the name is similar, so we have meth, meaning 1 carbon. Ane part is still there, so there's still that ANE, meaning it's singly bonded, and then OL is telling us there's an alcohol. So there's a lot in these little names. Ethanol is telling us 2 carbons, and means they're all singly bonded, and OL tells us there's an alkyl group on the end. So we have to start breaking apart these names and trying to figure out what this terminology is. It is learning a new language. So if you like languages, you are in for a treat, because we get a lot of new words and a big naming system here. So propanol, again, same thing. Prop is 3 carbons and is singly bonded. OL is the alkyl group. Butanol, 4 carbons, singly bonded, and an alkyl group is what it means. But again, they're homologous series. What a homologous series means is, again, they're 1 carbon, 2 hydrogens bigger, but they also have similar properties. So notice, here's our homologous group, and with our alkane chains, again, alkanes are just carbons that are singly bonded. Again, we have methane, ethane, propane, butane, pentane, and hexane. And notice they have heptane and octane here. The curriculum for standard level only has you go up to hexane. So I told you I'd warn you, stop right there. Don't worry about heptanes and octanes and nonanes and decanes. You only have to go up to 6. Okay, that makes some things a little bit easier. Higher level, we'll need to know some things beyond that, but for right now, let's just worry about the first 6. Okay, so what we see with homologous series is they have similar chemical properties with gradual changes within them. So, like this says, a gradation in physical properties. So similar properties, they have similar properties that do change slightly. So notice, if we have methane, we have a really low boiling point that steadily increases as we add carbons. And we know that from previous discussions of chemistry, that the heavier a molecule is, typically the higher its boiling point is. Again, if there's no other, if you remember this word, intermolecular forces. And these do not have intermolecular forces. These compounds, by the way, are all nonpolar compounds. They're symmetrical. They have no dipole moments or anything like that. So they have similar chemical properties. We see gradual trends within homologous series. So here's the key term. I believe it's a key term because there's a box here that needs a key. These are the keys. So successive members of homologous series, and there's lots of questions actually in the IB about which of these compounds are members of homologous series and what, are the similar properties of a homologous series. But they differ from a CH2 group. Members can all be represented. They have the same general formula. They have similarities in their physical properties that show gradual changes, and they have similar chemical properties. I'm sorry, we should talk about these separately. A gradual gradation in their physical properties and very similar chemical properties. Okay, it's nothing too hard. If compounds are made up of the same things with just a difference in a CH2, they're going to have similar chemical and physical properties. Okay, so now we're going to look at how we write these compounds. We have a couple different types of formulas. Now we have empirical formulas. Again, remember, empirical formulas are the smallest whole number ratio. And that works really great for ionic compounds. In organic chemistry, we do not see empirical formulas very often because that doesn't tell us very much. More often, we're going to see things written out as molecular formulas. Again, molecular formula is actually what's there. So the empirical formula is the smallest ratio. Notice 1 carbon, 3 hydrogens, but the actual molecular formula is 2 carbons and 3 hydrogens, which is much more useful for our purposes. So we want to know what empirical formulas are, but we're not going to use them very much. And also, I'll tell you this, we're actually not going to use molecular formulas very often because we like these condensed structural formulas. What these condensed structural formulas are is, again, it's a little bit of new language, but it tells us how things are bonded. So if we see CH3 groups, we know this is a CH3 group. If you see CH3, that is a methyl group. Okay, so there are 2 CH3 groups attached. This is what our full structural formula is going to be. So really what you want to focus on being able to do is recognize full structural formulas and be able to read these condensed structural formulas and write them as full. So being able to go back and forth between these is going to be very, very important. Notice there's just a lot of things that we need to know in organic chemistry that are new. Notice this compound. So we have that CH3 group. I recognize that as right there. I'll erase it so we can see the rest of it. And then we have the COOH. If I didn't know any better, I'll write it maybe COOH in the line, right? That kind of makes sense. But that's not what this is. This condensed structural formula is actually telling us what the full structural formula is, right? Anytime you see the COOH, that is shorthand really for this compound. This is a carboxylic acid. And that means it has alcohol on it and a double bonded oxygen. It causes this to react like a weak acid. So ethanoic acid is actually our acetic acid. It's our vinegar, and it acts as a weak acid. So that's another functional group that we need to know. And we'll look at functional groups here in a moment, but we just want to be able to interpret these condensed pieces into full structural formulas. Now, if you notice this one, and we won't worry about it right now, but this is crazy, right? This is glucose. C6H12O6 is typically how we've talked about glucose, but now that you are an organic chemist, congratulations, we'll actually have to know the structures of these, right? So we can piece this apart. It's not really as terrible as it looks. It looks, granted it looks terrible, but if we see a CHO, that is always this group, okay? And we'll get to the names of it later. And then notice inside is a CH with an OH group. So C with an H and an OH. And notice there's a 4 outside the parentheses. That says you have 4 of those. So 1, 2, 3, 4. And then notice on the end you have a CH2, that's this, with an OH attached. That's right here. So we can read what these mean. Again, it's not going to be easy when we start. Don't pretend it is. Don't be like, I can't do this. I never will be able to do this. You will. But I'm not going to lie, that will take some work. Reading the formulas, learning the names, writing the full structure of formulas is going to be just a whole... Actually, you should be excited. You have a lot of learning to do in front of you. It's fun when there's learning to do in front of you. It's not going to be boring. There's a lot of work. It's good. So that is the piece we want to start on, is the naming. Or the nice, fun chemistry word for naming is called nomenclature. So organic chemistry nomenclature. And you've named simple molecular compounds before, and you've named ionic compounds before, but our naming of our organic compounds, completely new. Okay? So first off, and this is definitely something you want to write down if you're taking notes, is these are our number of carbon atoms in our longest chain. So notice this is giving us rules for how to name compounds. This is number 1, identify the longest straight chain of carbon atoms. Okay, so this isn't necessarily the number of carbons in the total structure. This is of the longest chain, and we'll look at what longest chain means here in a moment. So the longest chain gives it its base kind of name. So if there's 1, it's a methyl group. 2 is eth, just like we said before. 3 is prop. 4 is but, or but, if you, well, that's but, no. It'd be nice if it was but and all, but, well, not that it'd be nice, just, never mind. Okay, pent and hex. And again, like I said, we just go up to 6. So that's not too terribly bad. And again, these prefixes are going to be if they have alcohols attached, or if they have carboxylic acids attached, or ketone, or anything. So meth, eth, prop, but, pent, and hex. Those are the ones you want to remember. And notice what else they say. It says, note that the straight chain doesn't necessarily refer to it being straight. Okay? It doesn't necessarily mean there's bond angles of 180, because remember, carbon compounds bond to 4 things. So they bond tetrahedrally. And so anytime we see a carbon chain, it's actually going to always have like these bond angles of maybe around 109.5, especially if it's a methane or an ethane. If it's an alkane and there's no double bonds or triple bonds or anything like that, we're always going to have these 109.5 bond angles. So what that means is we're going to have some kind of funny looking shapes occasionally, like these that are given from your book. Notice each of these, if our red pieces are carbon, we have 1, 2, 3, 4, 5 carbons. And this would be generally the way we think about this compound. So 5 carbons, all with hydrogens attached. We would call this pentane, right? That would be pentane. But notice, this is just a different rotation of the same molecule. So 1, 2, 3, 4, 5 carbons still. Notice this 3rd carbon, this bond is just rotated downward, which is completely fine. It doesn't mean it won't exist. It's actually probably both of them exist. There's a little bit more what we'd call, and this is something we'll get to, steric hindrance, some repulsion between the outside electron shells of these hydrogen orbitals if it is bent, but it could exist. So we'll probably see it more like this, has a straight chain, but this straight chain could still be bent, and it is still pentane. It is still the same structure. It's just a different rotation about those bonds. Notice this structure too has 1, 2, 3, 4, 5 different carbon atoms, so it is still, again, pent, and then ane, because they're all singly bonded. This one is rotated even more. So this number 5 carbon is rotated in as well. So again, just a different rotation about the bonds, which is perfectly fine. Again, we have these hydrogen atoms getting close to each other, so there's going to be some repulsion and some steric hindrance. So it's not going to be a favored structure, but it's possible. All right. Okay, so we know the numbers of our straight chains. Methyl, ethyl, propyl, butyl. What's after but? Pent and hex. Well, we try to know them. The other thing we are going to add to this is we're going to add to this some functional groups, okay? And so this is where, if you like flashcards, man, you get to make some flashcards, because this is where that fun piece comes in. So we have some functional groups to learn. Alkanes, okay, that ANE, if we have methane or ethane or propane, that means they're singly bonded. So the functional group, it doesn't give you a picture. It really should. It's just a single bond between all the carbon atoms, okay? If we have even one double bond in a structure between two carbons, then the ending becomes ene, okay? So we have propane here. If those carbons are double bonded instead of single bonded, even if there's just one of them, then it becomes a propene. So propane, propene, okay? Alcohol we already talked about in OL, so that would get tacked on the end. So propanol. And now, yes, if you're wondering right here, you could have a propanol. You could have a double bonded carbon here, and also an alcohol group on it. That is completely possible. So we can combine functional groups within the same compound. We're not going to do it yet. We're going to start with pretty simple things, but just so you're aware, it's possible. It could come. So we have alkanes, alkenes. We have alcohols, amines. Now, amines, this is, notice there's a little star. That's because this is a higher level. So if there is an NH2, then we have an amine. Notice it adds to the ending the name amine, which kind of makes it easier. So if we have propane with that NH2 at the end, it's a propamine on the end. That's kind of difficult to say. You have to practice it a little bit. Propamine, propanamine. There we go. I just need a little rusty. Okay, going on then, we have an aldehyde, which is a double bonded oxygen on the end, then with a single bonded hydrogen. And notice one thing they're leaving out that we do have to be careful of is, notice in a lot of these functional groups, they're leaving out the lone pairs that are like on the oxygen here or on the oxygen here, which is kind of not doing you justice, because sometimes when they want you to draw them, they want you to show all the lone pairs, all the carbon atoms, all the hydrogen atoms. So you want to make sure you know where those lone pairs are, because they are important and you can be marked off sometimes if you don't have those. Anyway, this is an aldehyde, so it ends in AL. It doesn't end actually in anal. It actually ends in AL. The AN part is because it's singly bonded here. So this structure is propanal because it is singly bonded with that aldehyde group on the end. So the important thing here is to be able to see this condensed structural formula and its name, and then how it looks. So those would be, well, I mean, you'd want a card with at least 4 things on it. An aldehyde is AL. It looks like this, and that's how you'll see it as a condensed structural formula. Notice next one is a ketone. And look at this. It's still a double bonded oxygen, but the difference is this double bonded oxygen is within the structure. So these R's indicate carbon chains that go out, okay? So this double bonded oxygen is on a carbon that's in the middle of the chain, as opposed to a carbon on the end of a chain. So things do get confusing sometimes. So ketone, again, isn't A-N-O-N-E. It's really just O-N-E, because that A-N has to do with the single bonded nature of the carbon species. So notice you'll see a CO within a group. That means it's a ketone. This one is propanone. Propan, because again, 1, 2, 3 carbons. It's all single bonded, so the AN, and then that ONE tells us there's a ketone in it. But we're not done. Okay, now we're going on to a few other things. Carboxylic acids. Ooh, I started shaking the whole world there. Carboxylic acids, double bonded oxygen, single alcohol group on the other side of it. OIC, and again, it's not an anoic acid. I kind of don't like that they include that. It's really an oic acid. Is a carboxylic acid is oic acid. Again, the ANE, it just means a singly bonded. So this is propanoic acid because, again, 1, 2, 3 carbons with that OOH on the end. And that is our carboxylic acid group. Notice amide has a star by it because it's higher level. Ester is a higher level. But we can see an amide, different than an amine now. An amine was just the nitrogen group. An amide is this nitrogen group attached to a carbon that has a double bonded oxygen. So this is a different group. And it ends in it is an amide, okay? An amide. So it's a propanamide. Again, 3 carbons with a double bonded oxygen there, and then that NH2. So amide, amine, both higher level things, as are esters. Esters is like a carboxylic acid that, again, is within a structure. Just like a ketone is an aldehyde within a carbon structure, ester is a carboxylic acid that is within the carbon structure. Notice this would be a carbon over here and a carbon over here. And it has an O8 ending. So I won't write the an, that's going to confuse you. This is an O8 ending. So the an, again, is from the single bonded carbon structure. But notice this one, again, 1, 2, 3. Now this has 4 carbons, but it's still a propanoate. Okay, it's still a propanoate because the longest carbon chain are these 3 carbons bonded together. This is where it's going to start getting a little bit tricky. And this other carbon is attached to the end right there. So it's not part of the full carbon chain. So still propanoate, but what is the carbon that's attached then to that oxygen? Is a methyl group, just a single CH3 group. So it's methyl propanoate. Again, we'll look at tons of examples. Right now we are just introducing functional groups, so we don't have to worry too much about it. Yeah. Okay. Nitrile is a triple bonded nitrogen to a carbon. It's a nitrile group, and so when we name it, it is just propane nitrile, just tacked right on there. So the name and the ending is all the same. That's actually a pretty easy one. That's standard level as well. Okay, and the reason, one other point on these, I said these are higher level structures, and they are. Standard level, you don't have to name amides, and you don't have to name esters, but here's the tricky thing. You have to be able to recognize them. So that's goofy. You have to know this is an amide. You have to know this is an ester. And back, you have to know what an amine is, but you don't actually have to name them. So it's a little goofy where you need to know them, but you don't need to name them. So I don't know how that works. So they are in the syllabus that you have to be able to recognize these in structures, but they're also listed in the syllabus that you don't have to directly name them. So kind of a goofy thing there. So I'm hoping that you have all your functional groups written down. You know, you have them on flashcards or what have you, so that we can memorize them. And then we're going to work a bit on naming. That is what we're going to spend our time on here for a while, because we can't go into organic chemistry until we really have our names down. So this takes a bit. In the syllabus, it says it should take 4 hours of class time. So, and that's just of class time. So, anyway. Now we're looking at the amide functional group. Again, this is a higher level functional group, higher level as far as being able to name it, but also standard levels being able to recognize it. So it's worth, for standard level, looking at this. Now notice, when we're talking about amide, so this is propanamide. So propanamide, the amide group, again, is the double bonded oxygen and then the NH2. So it's written as a functional group like this in a structure. So CONH2 is the functional group that is an amide. But now the goofy thing is you can have amides and you can have things attached where these hydrogens are, so these don't have to be hydrogens. So it gets it a little bit tricky. So this would be considered a primary amide because there is nothing attached. A secondary amide is going to have something else attached. And notice how we name it. Again, we'll get into more naming, a little bit more basic naming. This is just giving you some examples. And it kind of throws in these hard examples first. We probably should start easier, but it kind of gives you everything and then asks you to practice it. So now with a secondary amide, we have a methyl group attached. So it's a methyl propanamide. And the N in the beginning is telling us it's attached to the nitrogen, that methyl group is attached to the nitrogen. Otherwise, we would think it's probably attached to one of the carbon atoms. If we have two, this is called tertiary. If there's two carbons attached to that nitrogen, and then it would be NN di meaning 2-methyl propionamide. Okay, kind of confusing right now. That's about as hard as our naming gets, actually. So they throw out these really difficult examples at first, I think, just so you're aware that they're there. But we'll go back and we'll do some easier naming, actually, in our practice problems. I won't spend as much time going through this, but notice amines now can be the same thing. So we said amides, we could have things attached to these hydrogens. Well, we can in our amines too, and it's the same type of naming. We say N to say it's bonded to the N, to the nitrogen, and then whatever the group is. So a methyl group doesn't have to be methyl, but methyl propionamine, NN dimethyl propionamine, okay, same way. But this is more realistic of where we're going to start naming, especially at this standard level, what we need to know. So one thing, notice, the first thing we do when we name things is we want to find the longest chain. So if we look at this first example, there's 1, 2, 3 carbons. So we know it's a prop, A and E, because this is a single bond, this is a single bond. So it's propane, and then an OL tells us it's a propanol. Now what's different about this one than your standard propanol is that alcohol group is not on the end. If it was on the end, we wouldn't need that. It would just be propanol. But that alcohol group, lo and behold, found a new place to go. It said, oh, look, I can bond to the second carbon. Well, then we need to say that alcohol's on the second carbon. So it's a propan-2-ol. In the olden days, I would call this 2-propanol. That's how I learned it when I was just a little kid, a little chemistry kid, before I got acid burns, or my first acid burns. But now we put it in the name right here. Notice this. It's a little bit different. This has 1, 2, 3, 4 carbons, so it's a bute. Now they're not all singly bonded. They're singly bonded, but we have a double bond on the end. So this is butene. Notice they say 1. I think you actually can get away with just calling it butene if it's in the 1 position. If it was anywhere else, though, we'd have to put in that number. And notice they do here, so it's probably good practice to put it in no matter what. But I don't believe we have to if it's on the first position. And notice I started counting from this side because that's where the double bond was. If the double bond was on the other side, then I would start counting that. So I would start counting carbons closest to the first functional group. So in this case, butanoic acid, this would be my first carbon. 1, 2, 3, 4. I would count it in that direction. It's bute because there's 4 carbons, and because they're all singly bonded, and then oic acid because that's on the end. And so I'd write the CH3, CH2 because the CH2 group, and there's 2 of them, so maybe parentheses with a 2, and then COOH. That would be my condensed structural formula. And that's something you want to practice when you're going through these as well. Notice propanone. It doesn't have to have a number because it is a ketone. Ketone has to be in the middle. If it was a longer carbon, then we might have to start talking. So the last naming piece we need here is any side chains or substituent groups, mean groups that are attached. So if it's a 1 carbon, it's a methyl group because it's a 1 carbon. So if that methyl group is attached to a chain, we call it methyl. So this is a methyl propane because there's a propane group with a methyl attached. And we'll look at what this condensed formula means here in our next podcast. Ethyl group is 2 carbons, propyl group is 3 carbons. So that's not hard. We already know that it's meth, eth, and prop. That's not a problem. We could even have a butyl group or a propyl group, or a pentyl group or a hexyl group as well. Notice we can have halogens attached. They're fluoro, chloro, bromo, iodo. I don't think that's too terribly bad. I think we recognize that. And then also amino groups, which are nitrogen. So that are our basics of naming. What we're going to go on and do in the next podcast is we're going to look at the examples on page 374 and also the exercises, the practice problems that are there. So this has been an introduction to organic chemistry, pages 366 to 373 in your book, both 10.1 and 10.2.